All right, so a couple of examples we'll do with determinants, inverses, and what have you. The first one gives us this matrix here where A equals a nice square matrix, 5, 2, 3, 1. First option is to find the determinant. Remember, it symbolizes DET. And then the second one is to find the inverse. Remember, this is how we symbolize the inverse. So first off, we're going to find the determinant. Remember, determinant equals AD minus BC. So we're just going to substitute the numbers in place of those letters. So AD is, if you've forgotten, it goes A, B, C, D. All right, so AD is diagonally opposite each other, minus the other two diagonally opposite each other. So it's 5 minus 6, which is equal to minus 1. So because the determinant is not 0, that means that we can keep going to find the inverse. And if you remember how to find the inverse, it is 1 over the determinant multiplied to the front of, we swap D and A and turn, oops, not like that, sorry, D and A and turn B and C negative. So if I know what the determinant is, I can just quickly move things around and work out the answer. And it will look like this. It will be 1 over minus 1 multiplied by 1 minus 2, 5 minus 3. And the way you know it is that A and D have switched spots and B and C have become negative. And then don't forget to multiply the scalar into each position, and you will find 1 over minus 1 is just the same as minus 1. So everything will revert, or not revert, but everything will again change sign. So where B and C were negative are now positive, where A and D were positive are now negative. All right, one more example we'll look at. It has a rather scary question just there, but we'll get to that in a minute, and we'll talk through what we do prior. So first things first, let's find the determinant of this square matrix A. So determinant is AD minus BC. So it's 3 times 6 minus 2 times 1, which is 18 minus 2, which is 16. Again, because that's not 0, that means we can proceed to finding the inverse, which is question number 2. Remember, the inverse is found by 1 over the determinant multiplied by the matrix with the positions moved around and the B and C values changed to negative. So it should look like that. It should be 6 over 16. I'm going to need to make my matrix walls a bit bigger. Often happens when you do matrices. So 6 over 16 minus 2 over 16, 3 over 16, and minus 1 over 16. And you would simplify if you could. So 6 over 16 would become 3 over 8 minus 1 over 8. And I don't think the other two can be simplified. So that's the inverse. We don't need to take that any further. All we needed to know was the inverse, so we can leave that like that. Now the next one is this rather scary looking question here where it says to find x if we know that A times x equals this matrix here. So let's break it down and see what we can understand. So we know that A times x equals 5, 7. Now let's just ignore the possibilities with complicated matrix multiplication, and let's just try and get the x by itself here. So really, we'd have to divide by A. But as we've seen in finding the inverses, we know that dividing by this one thing is the same as multiplying by its inverse. So I'm going to erase this, and I'm going to say, if I was to multiply a times a to the power of minus 1 times a times x, and do that to both sides because I can't change one side without doing it to the other. All right, so this happens here. Inverse times something is just equal to 1, or in matrix, the identity matrix. All right, so we have I times x equals the inverse of A times 5, 7, or this funny matrix here. All right, so now all we have to do is do this side, and we've worked out what x would be, because I was, remember, just equal to 1 in matrix form. So we've got, here's the identity matrix here. So we're going to take, oh, sorry, not the identity matrix, the inverse. We're going to take this 3/8 minus 1/8 minus 1/16 and 3/16, and we are going to multiply it by 5, 7, like so. All right, now what you'll find is, remember that it's rows by columns, so it's going to be 3/8 of 5 plus minus 1/8 of 7. So I'll write it out for you. I don't expect you to do this off the top of your head. All right, so it's going to look like this: 3/8 times 5 plus negative 1/8 times 7. In that position there, notice there's no other column in the second matrix here, and this is where the order is important, all right, because we multiplied the inverse. Starting here, we multiplied it to the left, which means we multiply it to the left here as well. We don't just chuck it on the end, all right, so order was vitally important. This next one is going to be minus 1/16 times 5 plus 3/16 times 7. Oop, not supposed to put the matrix wall there. We'll put it here. All right, and what you will find is that this calculation is equal to 1, 1, which makes it nice and easy. And I'll show you another way we could have gotten there in case you're struggling with this or these fractions, which again, I don't expect you to know off the top of your head. Even I didn't know them. All right, so what we could have done, let's go back up to this step here. We could have left the inverse as this: 6 minus 2 minus 1, 3. All right, and then come down to this step here. We would have had the inverse, which was 1/16 matrix 6 minus 2 minus 1, 3, multiplied by 5, 7, like so. Then when I do the multiplication, I just multiply the two matrices first, like so. So 6 times 5, the 1/16 is just hanging out the front. So 6 times 5 is 30, plus minus 14, so 30 minus 14, and then minus 1 times 5, which is minus 5, plus 21. All right, and this will give you an answer of 16, 16, which you then multiply by the scalar out the front and get your way to 1, 1. So you need to remember that you don't always have to do this. Often it's easier to leave it in this form, because when you come to multiply it by another matrix, you're looking at whole numbers inside here rather than the nasty fractions that we had here. To recap this last example, it's really important that you see this process, because this question here uses really a combination of variable equations with matrix equations. All right, and it's important that you remember you can mix and match like that. So whatever you do to this side, you have to do to that side, remembering that you can substitute out matrices in place of variables at any point along the way. The other really important thing to remember is that normally when we try and get a variable by itself, we divide by whatever it's with. With matrices, there's no division. You must multiply by the inverse of what you're trying to remove. So this a here we need to get rid of, so we had to multiply by its inverse, which was why the question took us through the process of finding the inverse of a first of all. All right, and the final thing to remember is that the determinant will mostly be the first step, because if that is equal to 0, you can go no further and there is no point trying to find an inverse.